Now that you understand chemical reactions and the importance of balancing chemical equations, what about the weight relationships of these reactions? Suppose we were burning carbon from furnace tubes. This equation tells us that carbon combines with oxygen in the ratio of 3 moles of carbon to 2 moles of oxygen, and that 2 moles of carbon monoxide and 1 mole of carbon dioxide are produced. These mole proportions, in turn, indicate the ratio of the weights of each substance involved. The equation tells us that carbon and oxygen combine in a ratio of 3 times the molecular weight of carbon, or 36 parts by weight of carbon, to 2 times the molecular weight of oxygen, or 64 parts by weight of oxygen, and that 2 times the molecular weight of carbon monoxide, or 56 parts by weight of carbon monoxide, and 1 times the molecular weight of carbon dioxide, or 44 parts by weight of carbon dioxide, are produced. When you multiply the number of moles of a substance in a balanced equation by the molecular weight of the substance, you obtain a quantity known as the equation weight of the substance. The actual weights of substances involved in a chemical reaction are in the same ratio as their equation weights. Therefore, if we know a balanced equation for a reaction, and the actual weight of any substance involved in the reaction, we can find the actual weight of any other substance participating in the reaction. We use this proportion. Actual weight of one substance is to its equation weight as the unknown actual weight is to its equation weight. This equation may be written: the actual weight of one substance divided by its equation weight equals the unknown actual weight divided by its equation weight. The procedure for this calculation is to write a balanced equation for the reaction involved. Now write the known weight above the corresponding formulas. In this case, we will assume that we are going to burn 180 pounds of carbon. So we place 180 pounds above the carbon. Then place identifying symbols, such as X, Y, or Z, above the substances whose weights are to be determined by calculation. Be sure that the unknown weights are in the same weight units as the known weight. In this example, the weight units are pounds. We have already determined the equation weight of each substance involved by multiplying the molecular weight times the coefficient. Now place these equation weights below the proper symbols in the equation. We can now solve for the unknown weights of each substance involved in the reaction. First, we will solve for the pounds of oxygen required to burn 180 pounds of carbon in accordance with the equation. So write out the equation in this form: 180 pounds divided by 36 pounds equals X pounds divided by 64 pounds. Now we can solve for X, or the actual weight of the amount of oxygen to burn the 180 pounds of carbon. By multiplying 180 pounds times 64 pounds and dividing by 36 pounds, this shows us that 320 pounds of oxygen would be required to burn 180 pounds of carbon to carbon monoxide and carbon dioxide. We can calculate for Y, or the amount of carbon monoxide produced by the burning of 180 pounds of carbon, by again writing this equation: 180 pounds divided by 36 pounds equals Y pounds divided by 56 pounds. Y equals 180 pounds times 56 pounds divided by 36 pounds. Thus, Y equals 280 pounds. So 280 pounds of carbon monoxide would be produced by the burning of 180 pounds of carbon. And to calculate Z, or the amount of carbon dioxide produced by the burning of 180 pounds of carbon, we again write this equation. 180 pounds divided by 36 pounds equals Z pounds divided by 44 pounds. Z equals 180 pounds times 44 pounds divided by 36 pounds. The result shows the burning of 180 pounds of carbon will produce 220 pounds of carbon dioxide. The completed calculation shows us that 180 pounds of carbon burned with 320 pounds of oxygen yields 280 pounds of carbon monoxide and 220 pounds of carbon dioxide. But our burning operation is not complete, since a large quantity of carbon monoxide is formed, and this is undesirable. We would prefer complete combustion, which would be the burning of carbon monoxide to carbon dioxide. For complete combustion, an excess of oxygen must be present, so that no carbon monoxide is produced. And the equation would read, carbon plus oxygen yields carbon dioxide. We write the known weight, 180 pounds, above carbon, and place identifying symbols above the substances whose weights are to be determined. Thus, X pounds is placed above oxygen, and Y pounds is placed above CO2. We know that the molecular weight of one atom of carbon is 12, of one molecule of oxygen is 32, and one molecule of carbon dioxide is 44. Solving for X, or the amount of oxygen required to convert 180 pounds of carbon to carbon dioxide, we divide 180 pounds by 12 pounds, and that is equal to X pounds divided by 32 pounds. The result is 180 pounds times 32 pounds divided by 12 pounds equals X, or 480 pounds of oxygen required by our equation. Now we look at our reaction equation again to determine the setup for calculating how much carbon dioxide would be produced by burning 180 pounds of carbon. 180 pounds divided by 12 pounds equals Y pounds divided by 44 pounds. By multiplying 180 pounds times 44 pounds and dividing by 12 pounds, we find Y, or 660 pounds of carbon dioxide will be formed. Therefore, if sufficient oxygen is present, the carbon will be converted completely to carbon dioxide. This equation tells us that 180 pounds of carbon will react with 480 pounds of oxygen to produce 660 pounds of carbon dioxide. Now open your workbook to exercise 13. Now let's review some of the things we covered in segment 2. Valence is the number of electrons an atom will share, give up, or receive in combining with another atom to form a molecule. Covalence is the process of forming compounds through the sharing of electrons between elements. A pair of electrons shared between two atoms is called a covalent bond. Bonds may be single, double, or triple, according to the number of electrons shared. Electrovalence is the process of forming compounds through the transfer of electrons from one element to another. An ion is a charged particle which has given up or received electrons. Ions possess properties which are totally different from the atoms from which they come. Radicals are clusters of elements which behave as if they were a single element. Valence numbers may be positive or negative, but the net sum of the valence numbers of elements in a compound must be 0. The formula of a compound is a ratio of the number of atoms of each element present in the compound. The molecular weight of a compound is the weight of one molecule of the compound as indicated in the molecular formula. A mole of a compound is the quantity of a compound equal in weight to its molecular weight. The number of moles in a compound is equal to the actual weight of the compound divided by the molecular weight. A chemical equation is simply a statement of a chemical reaction using chemical symbols. When writing equations, the names of the reactants and the products must be known. The formulas of the reactants and products must be known. And equations must be balanced so that the same number of atoms of each element appear on both sides of the equation. When computing weights of substances involved in a reaction, the number of moles times molecular weight of a substance equals the equation weight of the substance. And the actual weight of one substance is to its equation weight as the unknown actual weight is to its equation weight. Now open your workbook to exercise 14.